Now moving on to this line, what we are having next is, so we talked about the inert gas condensation. Now from here we move on to physical vapor deposition. Physical vapor deposition is again a collective set of processes commonly used for, so physical vapor deposition. So physical vapor deposition is a collective set of processes commonly used for producing nanomaterial and to deposit thin layer of material, typically in the range of few nanometer to several micrometer. So you see here that whole deposition on the substrate is what is happening. So basically what you are doing, if I had to understand this whole technique, so you are creating a vapor phase, and so you are taking the material, you are creating a vapor phase and you are depositing the vapor on top of a substrate. So again, in order to take something into the vapor phase requires a significant amount of energy, and then you place it on the substrate. So you are forming layer or thin films on the substrate, and these are some of the techniques which are pretty extensively used in the electronics industry and all other manufacturing industries. Okay. So coming to the physical vapor deposition, so what you are doing is, which is also called PVD, is an environmental friendly vacuum deposition technique consisting of three fundamental steps. So you realize that you need conditions of vacuum in such situation, and the first thing is vaporization of the material from a solid source. This is step 1, vaporization of material from a solid source. This is step 1. Step 2 is transportation of vaporized material this is step 2, and the third step is nucleation and growth to generate thin films. So the whole area of thin films, thin film generation by nucleation and growth. So the whole area of thin film generation is dependent on these kind of physical vapor deposition. The most commonly used PVD methods are sputtering, followed by, it could be electron beam evaporation, electron beam evaporation. And you might wonder why I am highlighting these techniques, because if you have to appreciate the biological roots of synthesis, you will have to realize how much complex these processes are, how much energy intensive and instrument intensive these processes are. Pulsed laser deposition, and then you will be needing a vacuum arc. So this is what I was talking to you, pulse vapor deposition. So these are some of the ways by which physical vapor deposition works. Okay. Sputtering is a vacuum based PVD process which is often used to deposit films of nanomaterial, and sputtering works on the principle of momentum transfer, in which the atoms from the target, which is made up of the material to be deposited, are ejected by the ion bombardment. The deposition of material by sputtering can be achieved using DC pulse or direct current pulse, pulse DC or radio frequency. As I told you that you can use all these kind of energies, and the plasma of the natural gas, commonly argon, is generated between two electrodes by the collision of electron to the gaseous molecules. Ions present in the plasma are then accelerated towards the target by applying potential between the two electrodes, and these ions with appropriate energy thus hit the target, leading to the ejection of the material from the target. So, it is something like, if you follow this picture, okay, and the ejected material are then transported and deposited onto the substrate. So, you are basically making them travel through this nano slit or the aperture and getting them deposited. Okay. And there are two advantages: they lead to higher deposition rate and prevent target overheating and damage. So, this is what essentially the sputtering is all about. Similarly, you have electron beam evaporation, EBE technique. Okay. EBE or electron beam evaporation is a vacuum based, again all these are vacuum based PVD processes, pulse vapor deposition processes or physical vapor deposition processes, which is used to fabricate the thin films of nanomaterials. An EBE system consists of vacuum unit, electron beam source and target material. Again you see, you have a vacuum unit out here, as I showed you, aggregation zone, which is a vacuum unit. Then you have electron source, and then you have a deposition ground. So, the way it works is very simple. Electron beam hits the target and hit the target material. The target material atoms evaporates when temperature reaches above its boiling point, and evaporated material then transported, condensed on the substrate, and the advantage is again high deposition rate and can be used to deposit material ranging from conducting to insulating. And unlike thermal evaporation, electron beam evaporation can be used to deposit material of high boiling point. So, you are realizing that all these techniques, if I talk about all the physical forces I told you in the very beginning, it could be mechanical, it could be high energy radiation, it could be thermal, it could be electrical, it could be magnetic. So, using all these forces. So, in other words, if you logically breaks down the whole thing, what is happening is you have this bulk material and you are using all these different physical forces on this bulk material. Here is your bulk material, these are the physical forces, and you are applying the physical forces in most of this situation in a vacuum situation, and you are making thin films by depositing them, and all sorts of different kind of things what you are achieving by using these techniques. So, then we talk about the laser ablation or pulse laser deposition. Laser ablation methods utilizes high power laser beam. So, again here the physical forces is now laser, okay, and laser ablation method utilizing the high power laser beam that evaporates the particle from a solid particle. So, from the solid material. So, from here the evaporation is happening because of the laser beam. It is a very high energy laser. So, in normal laser ablation process, the laser can either be continuous laser or pulse laser. You could have a continuous source of laser or you can pulse it depending on what kind of evaporation pattern you want. So, laser ablation offers a flexible approach in the production of micro and nanostructure of polymeric materials. So, if you have to work with the polymers, what we will be talking about while talking about the applications. So, there will be lot of such applications of laser assisted or laser ablation technique or pulse laser deposition techniques. Okay. Then we talk about the vacuum arc or vacuum based PVD process, in which the arc is used to vaporize the material. So, you are using as a physical force, you are using a vacuum arc, which is again a very high energy process, and using the vacuum arc you are ablating the material, in which the arc is used to vaporize the material from for the synthesis of metallic, ceramic and composite nanomaterials and films. Okay. So, vacuum arc uses for metallic, ceramics, composites, whereas laser is used for polymeric and many other, of course. So, one of the areas is polymeric materials. Okay. Then you have laser pyrolysis. The laser pyrolysis technique is again a vapor based synthesis process. This method can be used to synthesize wide variety of nanomaterial like titanium oxide, silicon oxide, aluminum oxide, iron oxide, like TiO2, SiO2. So, you have following up where I told you. So, this is what we are talking about, laser pyrolysis, and laser pyrolysis could be used for synthesis of TiO2, SiO2, Al2O3, Fe2O3, and there are a series of other oxides and non-oxides like, so these are all the metal oxides, and among the non-oxides you are having silicon, silicon carbide, silicon nitride, molybdenum sulfide. There are a series of things which you could produce using laser pyrolysis. In this process, the resultant condensable product are generated from the laser induced chemical reaction at the interface of the laser beam and the molecular flow of gaseous vapor phase reactants. Okay. So, again the logic is the same. You are using different kind of high energy processes to generate these kind of nanomaterials. Similarly, you are having flame spray pyrolysis, which is flame or flash spray pyrolysis, which is the latest of all the flame aerosol technologies. It is one step combustion process where the precursor is in the liquid form. So, realize for this kind of things you have to have the precursor in the liquid phase. That is very essential. Your precursor is in the liquid phase. It is a one step combustion process where the precursor is in the liquid form with significantly higher combustion enthalpy, that is more than 50% of the total energy of combustion. Usually it is an organic solvent. The important technological element of this process include self sustaining flame, usage of liquid feeds and less volatile precursor, and it has very high scalability, high temperature flame and large temperature gradients. So, these are some of the techniques, some of the prerequisites for flame spray pyrolysis. Okay. In the same line, your next thing is the electro spraying techniques, which is this technique. Electro spraying is a technique similar to electro spinning, but it differs in the type of material to be produced. So, electro spraying is basically done for synthesis of nanomaterial, whereas electro spinning is being done for developing different kind of fibers. So, a lot of fibers, nanofibrous materials, especially the polymer fibers are being used or which are being used are produced by electro spinning techniques. But electro spraying on the contrary is a technique which is logically pretty much similar. It uses it is used for nanomaterial, mostly nanoparticle synthesis. Okay. So, coming back to the electro spraying techniques what we are talking about. So, your electro spraying is basically the electro spraying method is based on electromechanical device in which a mixture of solution. So, it is in the liquid phase containing the selected polymer and the solvent is taken up by a syringe and a high voltage is applied to the capillary tip that results in the production of charged droplets. Okay. The solvent is evaporated on its way to the counter electrode and particle or fiber are then collected at the end product. The electro spraying technique provides both flexibility and control of the surface parameters and electrospraying is one pretty neat process to produce nanoparticles. So, the last of this lot is melt mixing. So, melt mixing is essentially a method involved mechanical mixing of a polymer with modified nanofillers by extrusion or kneading, and less commonly by injection molding techniques. Okay. This is one of the oldest method to design polymer composites with nanoparticles. So, this is used for mostly the polymer composite development. And one of the oldest techniques available. Okay. This is one of the oldest methods to design polymer composites with nanoparticle as a filler to achieve desired material characteristic. This is most commonly used mechanical process because it is environment friendly and it is also well suited for current industrial practices. So, overall, this is what we needed to understand about the physical methods of synthesis of nanomaterial, which find applications for high energy synthesis using physical forces, as I have already mentioned. So, here you have the bulk material, which here is the bulk material which is exposed to these different kind of forces which are enlisted here, and the process what happens is these mechanical material abrasion, melting, evaporation, condensation, and this leads to the nanostructure formation. So, keep this key in mind. So, most of these techniques, if you realize, these are top down approach. You have a big material, you are bringing it down, smaller sizes. Okay. So, next what we will do, I will close in here. Next we will talk about the chemical and the biological mode of synthesis. Thank you.